Derivation of an expression for entropy of a reversible isothermal process. Now, entropy is the degree of randomness or disorderliness of a system, now, or of a molecule. Or if you want to derive an expression for the entropy of a system, you have to recall the first law of thermodynamics. And the first law of thermodynamics, you have it that the Q equals to the U plus the W. Now, for entropy, the U is still same thing as the E, which is the entropy of the system, the internal energy of the system. So the U, or what you have as the E, is equals to 0. Then we are left with the Q, which is equals to the work. Note, internal energy, you have internal energy, which is CV dt. So for an isothermal process, dt equals to 0. That makes the internal energy of the system to be 0. So from this now, the Q itself is P dV. So if I divide through by T, so that means I'm going to have the Q here over T equals to P dV over T. Now this dQ over T is known as entropy. So but dQ over T is our entropy. So from that you can just have it that the entropy of the system, from here now, instead of dQ over dt, we turn it to the X. Entropy equals to P dV over T. But from equation of an ideal gas, for an ideal gas, we have PV equals to nRT. So make P the subject of formula here. P now becomes nRT over V. Put that back into this equation. You have the X equals to, instead of P, it becomes nRT dV, all divided by V with what? T, which you have as the denominator. So at this point, T cancel T, then you have the X, which is the entropy, to be nR dV over V. So I can integrate both sides now. Integrating both sides, the left hand side, the X, if I integrate the X, I will integrate this other part, but as I go from 1 lower limit to 2 of nR dV over V. Now I can't integrate nR with respect to dV, so I'll